I just want you to see that our code is just going to compile. If we compile it now, let's do this. We're going to pass this through GCC. Okay, you see the build is good, and we have generated our binary, which is really not doing anything because our main function is just some dummy code we have here to make sure it works with C++20. But what I want you to see is that if you go in Bulldog, let's go in our Bulldog class and uncomment this class here, or this virtual method, we're going to see that we're going to get a compiler error. We have a squiggly line, meaning that we did something wrong. And let's look at the problems tab from Visual Studio Code here. Cannot override final function dog run. This is a final method from the dog class. If we try to override it further, we will get a compiler error. This is something we can achieve by marking our virtual method as final, as we are doing here. Now, if we try to build this program, we're going to get a compiler error. Let's pass this through GCC and let you see this. Okay, you see we get a compiler error, and the error is that we are overriding. Let's go up and see the error here. Error, and on line 12 in Bulldog H, we see that we are overriding a final method. Virtual void Bulldog is a final function, and we are overriding this, and this is going to give us a compiler error. This is the behavior we get. So the message here is that you can go in your inheritance hierarchy at any level and mark a virtual method as final and prevent downstream classes from specializing or overriding that method further. And if they do that, they will get a compiler error. This is something we can achieve in our C++ program. Another thing you can do with the final specifier is that you can prevent people from inheriting from your class altogether. Let's go to our cat class. I think that's the example that sets that up. We have a cat class. It is going to be inheriting from feline, but the class is marked as final. Now, what this is going to do, it's going to throw a compiler error anytime somebody tries to derive or inherit from this class here. So if somebody tries to inherit from cat, as we are doing here, create a wildcat from a cat, we are going to get a compiler error because we can't inherit from cat altogether. It is a final class at this moment. Okay, so let's look at our wildcat class. It is going to try and derive from cat. We can do something like this. We can remove our comments here. And if we try to do this, we will get a compiler error. Let's look at the CPP file and see what we have. It has nothing special. But if we try to do that and inherit from cat, we will get a compiler error because the cat class is final and you cannot derive from it. If you do that, you will get a compiler error because the cat class is final. This is what I want you to see here. Let's try and build our program again. We're going to pass this through GCC and we will see our compiler error. Okay, the build is finished with errors. If we go up, we will see that we cannot derive from a final base class. If we do that, we will get a compiler error. And this is what I want you to see here. Okay, now that we know this, we're going to take this back and take out the compiler error here because we want our code to compile. We're going to make sure it is compiling fine. Okay, now the code is compiling because we are no longer trying to inherit from cat. And I want you to now see a few interesting facts about the final specifier when it works together with virtual functions. Let's go to the main CPP file and show you the first fact. And that's that you can create a class right away and mark that as final as you create it, as we do here. If you do that, this class is going to not be inheritable. And if you try to inherit from it, you will get a compiler error. Let's take out everything we have here and just say hello in our main function. This is going to do just to have something. This is going to give us a compiler error because we can't inherit from a final class. Let's build and show you the compiler error. This is going to go through GCC and the build is going to finish with errors. And we have our message here, and we don't have the error we expected because we forgot to put our closing semicolon on our class definition here. But we can build again and get our error. Okay, the build is finished with errors, and the error is going to be that we cannot derive from a final class. This is what we expect here. Let's comment this out because I just wanted you to see this fact. Another interesting thing C++ allows you to do is to set up a new virtual method in a final class. Let's first build and make sure the compiler error here goes away. And I am going to show you that. Okay, the build is good. Let's go back in our final class, which is the cat class. If I remember correctly, this is the final class. We can't derive from this class, but we can set up a virtual method. For example, the virtual method here called meow is useless. Why is it useless? It is a virtual, and marking it virtual means that you at least want people inheriting from this class to inherit it and use it. Or even better, you want them to have the ability to specialize or override this method and make it do more specialized things. But you can't really do that because you can't derive from this class altogether. So this is something that C++ allows us to do, but this is a useless method which will never be used in any way. So this is something I want you to be aware of, but this is going to compile. Again, let's pass this through GCC. You're going to see that this is going to compile and work. Even if this method is really useless, I want you to be aware of this. Okay, so the build is good here. Okay, so this is our interesting fact number 2. Okay, even if this method is useless, it is possible to specialize a method coming from upstream classes from your final class. For example, in Feline, we have a method called run, which was introduced there, I think. We can override this method in our final class, which is the cat class here. So this method is going to be useless because it will be specializing what we get from our upstream class. This is going to work. Okay, so since we are looking at a few useless things you can do with final combined with the virtual mechanisms in C++, I want you to see that it is possible to set up a virtual method and mark it as final in the same declaration. And we're going to go to the bird class and really show you that. For example, we have a virtual method which is called fly, but this is marked final the moment we declare it. And this is going to be contradicting. For example, the virtual keyword means that people downstream will be able to specialize this or inherit this, but at the same time, we are marking this guy as final. So we are saying nobody downstream will be able to override this method. If they do that, they will get a compiler error. Now, which one is going to win, virtual or final? Final is going to win because if you try to override this method in downstream classes, you will get a compiler error. Let's go down and look at one bird we might have in our program. For example, we might have a pigeon. Let's grab this method and try to override it. You're going to see that we get a compiler error. We can go in pigeon and put in the fly method. And for example, we're going to say pigeon fly here. And we're going to say override. We are trying to override this method, but we're going to get a compiler error. You see we have a squiggly line because this is a final method. And we are trying to override this in a downstream class. And this class is a downstream class from bird. And in bird, we marked this method as final, so this is not going to work. Even if this is virtual, you want to be able to really use the virtual mechanism because this is final. If we try to inherit from this, if we try to override this like we are doing in Pigeon here, we will get a compiler error. Let's try and build our program and we will see that we get our trusty compiler error. The build is going to finish with errors. And if we go up, we're going to find our error. We're going to say virtual function fly overriding final function. We are overriding a final virtual method. And this is going to give us a compiler error. We can't do this. This is something you can't do in your C++ program. So this is really confusing because in bird, the virtual keyword suggests that you can really specialize this in downstream class, but this is contradicting, and C++ allows you to do this. You need to be aware of this. Again, if we don't override this and leave this in, the code is going to compile, but in my opinion, this is really confusing and you need to be aware of this. That's the whole point of this lecture here. Let's make sure the code is building, and this is really all I had to share in this lecture. Introducing the final keyword to you. You can use it to restrict how people override your virtual function, or you can use it to restrict people from inheriting from your class altogether, and use these things if they make sense for whatever application you are designing with C++. We are going to stop here in this lecture. In the next one, I am going to show you a secret you probably didn't know. So go ahead and finish up here and meet me there. In this lecture, we're going to explore how virtual functions or polymorphism plays with default arguments. And when we say default arguments, we mean a setup like this. We have a virtual function here, which is called add. It is going to return double, and it has default parameters here for a and b, and the value is 5 here. In our derived class, we also have the same function. We are overriding that, and we have a different set of values acting as our default parameter here. We are using 10 for a and b here, and we want to see how this plays with polymorphism. Now, please note that with polymorphism, if we go through a base pointer to manage a derived class object, what we want is to call the most specific implementation of the virtual function here. For example, if we have a base pointer managing a derived object, and we call the add method from a base pointer, we will get the most specific method here called. But what you get with these default arguments is that the compiler is going to use static binding to decide which default parameters to pass to your function. So even if you will get this method here called, the compiler will still use the default arguments we have in our base class. So we will call this method here, but we will use the default arguments coming from the base class, and this is a behavior you need to be aware of. Okay, so another way to put this is that default arguments are handled at compile time. The compiler is going to wire these things at compile time where you are building your application, and the virtual functions are called at runtime with polymorphism. So if you use default arguments with virtual functions, you might get weird results with polymorphism, because the default arguments you will be using are going to be decided by static binding, but the actual function that you get called is going to be decided by dynamic binding. So we will call the virtual function in our derived class, but we will be using the default argument from the base class. This is the behavior we'll get. You need to be aware of this and make sure this is what you desire. My personal preference is to not use default parameters or default arguments with virtual functions, because this is really going to make my code hard to follow and hard to understand, especially for other developers that might have to work on my code base in the future. Okay, here is a simple example. We have a base pointer which is going to be managing a derived object, and we will call the add function here. What do we expect to get? Well, because we have polymorphism here, we will call the most specific add function here, and that's going to be the add function from our derived class. But the default argument we pass are not going to be decided by the derived class. The default arguments are going to be plugged in at compile time using static binding. So because the base pointer is a base object, we will be using the default arguments from the base implementation of the add method. So we will just plug in 5 and 5. So we will add 5 to 5 and add a 2. That's why we get a 12 right here. And if we go through base references, we will get the same result, because this is going to enable or trigger polymorphic behavior in our C++ programs. If we go through direct objects, we will be doing static binding, and we will use the default arguments or default parameters from our derived object. And remember that we use the value of 10 in there, so we are going to add 10 to 10 and add a 2, and we are going to get a 22, as you see here, through static binding. If we do slicing by assigning a derived object to a base object, the derived information is going to be sliced off. And if we add, we will use the default parameters from the base class, and we will use the implementation in the base class. So if we come back to our code here, we will use the default arguments from the base class, and that's a 5 and a 5. We're going to add them up because the body is going to be from the base class. Remember, the derived information has been completely sliced off. So we are going to add a 5 and a 5 and a 1, and we're going to get 11 printed out if we do slicing. And that's the result we get right here. As a closing note before we head over to Visual Studio Code, again, the default arguments with virtual functions can be very confusing. They are best avoided because they really are going to give a hard time to anybody that is going to be working on your code in the future. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is virtual functions with default arguments. We're going to grab the code from our template project. We're going to copy this and put this in the current project. And I am going to grab my classes, base and derived that we are going to be using here. If you don't want to type along, you can grab the source code from the resource section of the course. If you don't want to type all these classes or create them, you can grab the source code from the resource section. On this lecture, you're going to download this and use this. You don't have to waste time typing these things because many of these things are already familiar to you. We're going to open this in Visual Studio Code and we're going to have our classes here. We have a base class, which is going to have a virtual function with a pair of default arguments here. We are using 5 in our add virtual function here. And if we go in derived, it is going to derive publicly from base, and it is going to override our virtual function here. But notice that it is going to set up its own default parameters. So if we do polymorphism and use a base pointer to call the add method here, we will get the most specific or the most specialized version of the add method called, and this is going to call this body here, but the parameters are going to be decided by static binding. So because we will be going through a base pointer, we will use the default arguments from the base class. That's going to be 5, and we're going to play with this and see what this is going to give us in the main CPP file here. Let's clean up a little bit. We're going to remove whatever we don't need here. And we are going to include our derived class. We can do that. We are going to put in our code to really play with us. Let's remove these spaces because we don't need them. We are going to go through a base pointer to manage a derived object. And this is a setup we can use to put things in place here. We are going to call the add method. Notice that we are not passing in any parameter because we are going through a base pointer and the add method is virtual. Polymorphism will kick in and we will get the derived version of our add function called. So we will call this add function here, but be careful because we won't be using these default parameters here. If we did, we would add a 10 to a 10 and get a 22 in our main function here, but that's not going to be the case. The compiler is going to use static binding to decide which default parameters to use, either those in the base class or those in the derived class. And notice that if we hover over this add function, you see that the compiler has plugged in those from the base class, and that's what the compiler is going to do. So it is going to add a 5 to a 5, and it is going to add 2 to that. I think that's what we are doing in our derived version, and we are going to get a 12 printed out. Let's build and see if this is actually the case. We're going to pass this through GCC, and that's the compiler. That is our favorite now. The build is going to be good. We can close this and bring up a PowerShell window. And if we run Rooster, we're going to see that derived add was called and the result was 12 here. This is what we get. Again, the compiler is going to call the most specialized virtual function override here, but it is going to use the default parameters from the base class. You should really know this. And this can really be confusing, especially if you are a beginner to polymorphism. If we go through a base reference, we will also get polymorphic behavior. So if we have a derived object and we set up a reference to that, which is of type base, and we go through that base reference and call the add method, we will get the most specialized add version called. So that's going to be derived add, but we will use the default parameters from the base class because which default arguments we use is decided by using static binding, and that's what we get here. And Visual Studio Code is really helpful here because if we hover over the add function, we're going to see which default parameters were plugged in by the compiler, and you see that they are those from the base class. So we are again going to add 5 to a 5, and we are going to add a 2, and we will get 12 printed out here. If we build and run, we're going to see that this is the case. The build is good, we can clear and run Rooster. We're going to see that with a base reference, we're also going to get a 12. We will get the most specific implementation of the add method called, but we will plug in the default parameters from the base class. I really want this to be super clear. If you set up things in a way that you are going to get static binding, then if you are going through a base object, you will call the base version of the add method and you will use the default parameters from the base class. If you happen to be manipulating a derived object, you will use the information in the derived class. The derived version of the add method is going to be called, and we are going to use the default argument from the derived class. So if we set up another example here, we can set up a base object, for example. We're going to say base and say base 3. We can do that. And we try to call the add method. We can say base 3 and say add. We can try and store this in our result variable and we can print this out. We're going to say stdcout row result. We can say something like this and we're going to print out the result here. If we build and run, we're going to see that this is going to call the base version of the add method and it is going to use the default parameters from the base. If we go back to base, we're going to see that we are going to add a 5 to a 5 and we will get 11 because we will plug in a 1 and return the result here. Let's build and run and see that this is actually the case. So this is going to be completely doing static binding. Let's clear and run. You see that the build is good. We're going to run Rooster and we will get 11 printed out here. Hopefully you can see this. If you assign a derived object to a base object, you will get slicing. Let's see that we can actually do this. But before we do that, I also want you to see that you can also do row direct objects of derived classes. If you do this, you will get the information from the derived class. We will use the body from the derived class and we will use the default parameters from the derived class. So we will take 10 and add a 10 and we will add a 2 to that and we will get a 22 printed out. I think we can do this. So let's put in a separator because that's going to make it easier to follow these things. And we're going to build with GCC. The build is going to be good. Hopefully the build is good. We can clear and run Rooster and we're going to see that we get a 22 here. If we assign a derived object to a base object directly by doing something like this, I think we don't need this guy here. We can remove this. We have a base object that we are setting up here, and we are assigning a derived object to this base object here. If we call the add method, we will get the version from the base class because, mind your steps, this is going to slice off all the derived information because we are not going through any kind of base or reference. So this is going to slice off all the information we have in the derived object here and we will be left with the base information. And if we call the add function here, you see that we are using the default parameters from the base class and we will use the body of the base class implementation here. So we will add a 5 to a 5 and we will add 1 to that and we will get 11 printed out as we see here. Let's build and actually prove this. We're going to pass this through GCC. The build is going to be good. We can clear and run Rooster and we are going to see that the result is 11 if we do row object assignment here. This is really all I wanted you to see in this lecture, that you should really be careful if you are using virtual functions mixed up with default arguments. The compiler is not going to do dynamic binding on the default parameters. It is going to decide which default parameters to plug in at compile time using static binding. So the compiler is basically going to look at the type of the pointer or object that you have, and it is going to use that to decide which default parameters to plug in. So at this example here, for example, at line 7, it is going to see what kind of pointer do I have. I have a base pointer, so I am going to use the default parameters from the base implementation. And if you hover over here, you're going to see that it is going to plug in a 5 and a 5. Even if we are using the most specialized add version in our inheritance hierarchy, the compiler is going to still use the default arguments from the base implementation. Down here on line 16, the compiler is going to say, which kind of reference do I have? It's going to say base because that's what we have here. So it is going to use the default parameters from base, and that's what it is going to plug in here, 5 and a 5, and we're going to get this result here. Down here on line 25, the compiler is going to see which kind of object do I have here. Base3 is a base, so I am going to use the default parameters from base. Down below on line 31, the compiler is going to look and see which kind of object do I have here. The object is derived, so I will plug in the default parameters for derived. Again, this is really what the compiler is going to do. With default parameters, the compiler is never going to do dynamic binding. And this is going to make your code really confusing. Again, my advice is to avoid default arguments or default parameters if you are using polymorphism in your inheritance hierarchy. We are going to stop here in this lecture. In the next one, we're going to learn about virtual destructors. Go ahead and finish up here and meet me there. In this lecture, we are going to explore virtual destructors. And these are destructor methods you might want to be called using dynamic binding or polymorphic behavior. We are going to be using this inheritance hierarchy to play with things. So the animal class is going to be our base class. We are going to derive from that publicly and have a feline class. And we are going to derive from feline and have a dog class. This is the setup we are going to be using here. Now let's look at some code. We are going to set up our animal class like this. Nothing really special here. Notice that the destructor is a regular destructor we have. We will derive from animal and create a feline class, which is going to set up its own virtual function, which is going to be run. If you want, you can override the breathe method, but we don't want to do that here because we just want to focus on the destructors here and the order in which they are going to be called. We are going to derive from feline and set up a dog class. And this dog class is going to set up its own virtual function. And notice that it has a destructor, which is really a regular destructor. Now, once we have this inheritance hierarchy set up, we might want to do something like this. We can create a dog object. And when it is time for this object to be destroyed, I want you to focus on the order in which the destructors are going to be called. We have seen this before. The destructors are going to be called from the specialized to the most base implementation of the destructor. So the destructor for dog will be called first, then we will call the destructor for feline, then we will call the destructor for animal. Now, a problem is going to pop up if we are using a base pointer to manage a derived object with polymorphic behavior that we might want for our inheritance hierarchy here. So we are going to use an animal pointer to manage a dog object like this. And when it is time to release the memory for this object, we may be tempted to call the delete operator on our animal pointer here. But this is only going to call the destructor for the base class. And hopefully you can see the problem here. Because our destructors are not virtual, the compiler is going to use static binding to decide which destructor to call. So it is going to look at the type of our pointer, it is going to see that it is an animal pointer, and it is going to decide to call the destructor for animal here. That's why we get this result. We are managing an object which is not just an animal, it has derived information in it, but we are only calling the destructor for the base part of this thing. So any piece of dynamic memory we might have allocated in the constructors for feline or dog is going to be leaked out. Because remember, even if this is a dog object, it is made up of base parts. The foundation for this is going to be animal. And on top of that, we are going to build a feline level. And on top of that, we are going to build a dog level. In this case, only the destructor for dog is going to be called. And any dynamic memory that might have been allocated at the feline and dog level is going to be leaked out. And this is something we don't want. You really need to keep your eye out on this. And this is something really bad. You really need to keep your eye out for this. So this is a really big problem. And to solve it, we need the destructors to be called using polymorphism. And you can set that up by marking your destructors as virtual. If you do this, the compiler will know that if you are going through a base pointer to manage a derived object, when the time comes for the memory to be released and you release the memory through a base pointer, the compiler is going to call the most specific destructor it can find. And this is going to solve our problem. Then we will reuse the order we are familiar with. The most derived destructor will be called, and it will call its base destructor, and that's going to happen until we hit the most base class in our inheritance hierarchy, and memory is going to be released exactly as we would want. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. We are going to learn about virtual destructors, and before we do that, we're going to grab our template files and put them in place. Let's do that. And I am going to put in the classes that make up our inheritance hierarchy. Our most base class is going to be base. Our most base class is going to be animal. After that, we're going to derive. We are going to derive from that and create the feline class. And we are going to derive from feline and create a dog class here. This is the inheritance hierarchy we talked about in our slides. Okay, we are going to open this up in Visual Studio Code, and this is going to give us our classes here. And we are going to remove these virtual keywords because we want to see what would happen if you don't mark your destructors as virtual. We're going to do that for feline. We're going to do that for dog. Let's remove the virtual keyword here. We're going to remove that, and we're going to remove that for the animal class. And we want to see the implementations for our destructors. For animal, we are just going to say that the destructor for animal was called. For feline, we're going to say the same thing. Feline destructor called. For dog, we're going to say the same thing. We're going to say destructor for dog called here. We are using strings as our parameters here. So I think it is a good idea to change these guys to use string view. I am going to do that and come back when this is done. Okay, this is done. All our parameters are of std string view type. And now that we have this inheritance hierarchy, let's make sure none of the destructors is virtual. This is the case here. We can head over to the main CPP file and use this inheritance hierarchy here. We're going to crack it open and remove whatever we don't need here. We are going to include our dog class, which is going to implicitly include or its parent classes. So we're going to include dog.h here. And we are going to create a raw dog object by default here. We're going to say dog, and let's say dog1. We can do that. And we might not even give it any parameter. This is going to call the default constructor. And if we go to dog, we're going to see that it is possible to specify information here, first style, description, but we're going to ignore this. And we just want to see which order in which the destructors are called. Let's build and run this program. We're going to pass this through GCC. The build is going to be good. If we clear, let's bring up a PowerShell window. To do that, we're going to clear and run Rooster. You're going to see that dog destructor was called, feline destructor was called, animal destructor was called, and this is really cool. This is the order we expect by default. But if we don't do something like this and say animal pointer and say p animal to mean a pointer to animal, and we say new dog, we're going to allocate a dog on the heap, and we're going to manage that using a base pointer. And if we try to release the memory here, let's do that. We're going to say delete p animal. Let's see which destructor gets called here, because notice we are using a base pointer to manage a most specific object here, which is a derived class of dog indirectly. And we will see that we don't get the destructors called in the order that we expect. Let's build and run this program to really see this. We're going to use GCC to build it. The build is going to be good, as you see here. We're going to clear and run Rooster. Now you see that only the destructor for animal is called, even if we are really managing a dog object. For things to work really well, we would expect the destructor for dog to be called, and then the destructor for feline, and then the destructor for animal to release or the memory that might have been allocated by these parent classes for our dog class. If you go back in the CPP file, for example, for each of these classes, you're going to see that the compiler is going to be calling each base class of the current level that we are at. In dog CPP, we are going to call the constructor for feline. The constructor for feline is going to be called if it is doing any dynamic memory allocation. We need to release this memory. Constructor for feline is also going to call the constructor for animal. And if animal is doing any dynamic memory allocation, this is going to need to be called. But notice that we are just calling the destructor for animal. And if we only call this destructor, all of the memory that was allocated by the feline constructor is going to be leaked out because only the animal destructor is going to be called. Hopefully you can see the problem here. But this is not the only problem. The C++ standard says that if you do something like we are doing here and call a destructor using a pointer to the base class, but that pointer happens to be managing a derived object, this is going to give you undefined behavior. So you're not guaranteed to get to the same behavior on different compilers, on different operating systems. So this is something really bad. We want all the destructors in our inheritance hierarchy to be called to properly release the memory that would potentially be dynamically allocated by each level in our constructor calls. The fix for this is really simple. All you have to do is mark your destructors as virtual, and the compiler will call the most specific destructor for your classes. So all we need to do is go in and mark these guys as virtual. So we're going to do that. The base class destructor is going to be marked as virtual. We're going to go to feline and do the same thing. We're going to mark that as virtual. And we're going to go to dog and mark its destructor as virtual. We're going to do something like this. And now notice we don't need to change any other thing. If we build our program, we're going to pass it through GCC. It is going to do exactly what we want because now the compiler will resolve the calls to the destructors polymorphically. Because we are going through a base pointer, the compiler will call the most specific implementation for the destructor. Because we are going through a base pointer to call the destructor here, the compiler will call the most specialized destructor we can find. And it is going to find the destructor for dog, which is going to be the most specialized destructor we can find in our inheritance hierarchy. It is going to call the dog destructor. That's going to call the destructor for feline in turn. And then that's going to call the destructor for animal. And our memory is going to be released properly. That's what we're going to see here. Let's make sure we build this again because I'm not sure if I actually built this. The build is going to be good anyway. So we're going to clear and run rooster. Now you see that the dog destructor is called, the feline destructor is called, the animal destructor is called, and everything is just going to fall in place. So my advice, if you are using virtual functions in your inheritance hierarchy, make sure you also mark your destructors as virtual. This is going to save you future headaches you might come in contact with if you are using a base pointer to manage a derived object and you are doing some kind of dynamic memory allocations in your constructors. That's going to release the memory properly if you are releasing the memory through a base pointer like we are doing on line 8 here. This is really all I had to share in this lecture. I hope you found it interesting. We are going to stop here in this one. In the next one, we're going to learn about dynamic casts. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about dynamic casts. And the dynamic casts are a facility we have in C++ to do downstream transformations between our polymorphic types. So if we have a base pointer, for example, we can transform it to a derived type and be able to use it like we use any raw object. For example, if we do this kind of transformation, we will be able to call non-polymorphic functions, and this may come in handy sometimes. This is the hierarchy we will be using. Our top class will be animal here. We will derive from this and create our feline class, and we will derive from feline and create our dog class here. If we have a base pointer pointing to a dog object, for example, the most specialized class we can have in our inheritance hierarchy, sometimes we might want to transform from this base pointer to the most derived object here and get the direct most derived object that we can really call anything on. If you remember, with a base pointer like animal here, the only thing we can do is really call polymorphic or virtual functions. But sometimes we want to do much more than this. For example, if we want to call non-polymorphic functions, this is not going to work because the base pointer has no knowledge of those functions. So if we need to do that, explicitly transforming from a base pointer to a derived pointer is going to give us that capability if the actual object we are pointing at happens to have that method. Okay, so this is what we are after in this lecture. We want to be able to transform from a base class pointer or reference to a derived class pointer or reference at runtime. Another way you can take this is to think of the base class pointer or reference as input, and we want to get a derived class pointer or reference as output in our C++ program. And the main benefit of this is to be able to call non-polymorphic methods on derived pointers or references. This is going to be super cool in some cases. Okay, so let's look at our inheritance hierarchy here. The top class is going to be animal, as you see here. It's going to have a single virtual method. It's going to also have a virtual destructor because we know how to do this now. We can derive from this and create our feline class, which is going to be inheriting publicly. It's going to have its own run method, and it's going to declare its own other method, which is not virtual. We can also derive from feline and create a dog class. This is how we do this. And we're going to set up our own virtual method in dog, which is going to be bark. And we can really do anything we want with this inheritance hierarchy. Okay, what we're going to be using as input is a base class pointer or a base class reference, and we set them up here. This is our base pointer, this is our base reference. And we want to go from these and create a derived class pointer or reference that we can use to even call non-polymorphic functions. And we can achieve that using dynamic casts. Here we're going to show you how you can cast pointers. Again, our animal base pointer is going to act as our input, and the output is going to be what we want to get out of this transformation. And all we do is say dynamic cast. We specify a pair of angle brackets. Inside, we're going to specify the output we want to get. And this is usually going to be a derived class pointer. So the base class pointer is going to be within this parenthesis, and it's going to be our output. And this is going to do the transformation, and it's going to give us a result that we're going to be storing in our feline pointer here. And if this succeeds, we will have a valid feline pointer here, and we can use it to call non-polymorphic or non-virtual functions like we are doing here. And this is super cool. Another thing you can do with this is use the result of this transformation in a pointer check. For example, we can check and see if this pointer is not a null pointer. If it's not a null pointer, we can call our non-polymorphic function to it. The result was successful. But if it's null pointer, we're going to fail and fall down here, and we can say that we couldn't cast to a feline pointer. And some of you might ask, how can this transformation fail? Well, if we go back to our code here, we have an animal base pointer, which is really pointing to a feline object in memory. If we try and cast this animal pointer to dog, suppose we want to do this kind of transformation, try to think about this. This is not going to work because we really have no dog information in this feline object. And if we try to cast this to dog, the compiler will really have no way to do this, and the transformation through dynamic cast will fail, and we will say the message here, meaning that we couldn't do the transformation the user asked for. So here we can do the transformation and transform from a base pointer to a derived pointer, but we can also transform to a derived reference. And I am going to show you the syntax to do that, and it is super simple. We say dynamic cast and we specify our input reference. Notice that this is a reference you have to put in, it's not a pointer, and you specify the output within this angle brackets here. Once you do this, the output of this is going to be a derived reference, and we're going to store this in our feline reference here. Once we do this transformation and the transformation is successful, we're going to be able to call our non-polymorphic function, and this is going to work. But with references, we don't have the luxury to do something like a pointer check because there is no such thing as a null reference. A reference is always pointed to something, and if the transformation fails, we will have some kind of invalid reference. And if this fails, it is probably going to blow up and give us undefined behavior. So you don't really want to do this. I usually don't recommend doing this kind of transformation with references unless you know that the transformation is possible beforehand. What I usually recommend is to pass-through pointers, and it is even possible to transform a base reference into a derived pointer, and the syntax to do that is what you see here. Okay, and once we do a transformation to a pointer, if the transformation is successful, we're going to have a valid pointer in here. If the transformation fails, we're going to have a null pointer, and the check is going to draw us here, and we're going to print this message to say that we can't do the transformation here. Okay, again, the cast may fail. If it fails while we are trying to transform to a dog pointer, we are going to fall down here and say that the cast failed. We can also do the same thing through references. For example, if we want to transform this base reference to a derived pointer, and this fails, we're going to fall here because of the check we are doing here. We can do something like this to make our code much safer to work with. And another thing I should really point out is that in practice, casting like this is usually done in functions where you are passing a base pointer or a base reference as a parameter. And in this function, you somehow need to call a non-polymorphic function. So you might do something like this and take the pointer and turn that into a derived pointer. And if the transformation is successful, you're going to call your method. And if the check fails, you're going to fall here and print an error message. You can do something like this with pointers, and we can do exactly the same thing with references. But here, because we want to do this check, we're going to transform our base reference into a derived pointer and call our method on the derived pointer instead. This is going to give us the ability to do this kind of check to make our code much safer to work with. A word of caution here, overusing downcasting is a sign of bad design. If you find yourself doing this kind of thing a lot to call non-polymorphic function, that may be a sign that you should make that non-polymorphic function polymorphic, because that's going to save you from doing this kind of transformations a lot. Just make sure you don't overuse this and do it in a few cases where you really need to do this kind of thing. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is Dynamic Casts. We're going to grab our template files and we're going to put them in place. Let's do that. And we are going to grab the files that make up our inheritance hierarchy. We're going to put those in. We have animal, dog, and feline. And this is going to make up our inheritance hierarchy here. Once we have this in place, we can open this up in Visual Studio Code by dragging and dropping here. And this is going to give us our files. Okay, we have our files in here. We can open up the animal class, which is our base class. We can see that it is really simple. It's just going to have one virtual method, which is breathe. It's going to have a single member variable, which is description here. We can derive from this and create our feline class, which is going to inherit publicly from animal. Feline is going to set up its own method, which is non-virtual, and we will have a virtual method called run. We can override in downstream classes if we want to do that. And let's look at the implementation for feline CPP. If you want to do that, you can take a look. It's just going to forward the construction to the base class to build the base part of us. Let's look at dog. Dog is going to inherit from feline, and it is going to set up a simple virtual function called bark, and it's going to have a virtual destructor. Now we know that we should really put in virtual destructors if we happen to even have a single virtual method in our inheritance hierarchy, because that's going to make things easier. Now, we want to go to the main CPP file and play with dynamic casts. We're going to remove whatever it is we don't need here, and we can include our most derived class. Let's include dog here. This is going to implicitly include both feline and animal, because this header is going to include its parent, and its parent is going to include its own parent. This is the logic here. We are going to start out by using a simple example here and show you that you can't really call non-polymorphic functions from a base pointer that is managing a derived object. And here we have an animal pointer. It is a base pointer, and it is managing a real feline object in memory. But if we try and call a non-virtual function through this base pointer, this is going to blow up. This is not going to work because we can't really call a non-polymorphic function through a base pointer, because that's not a virtual function. The requirement to be able to do this is for the function to be virtual, and do some feline thingy is not a virtual function that we know at the base level. So this is not going to work by default. And if we try to build code like this, this is going to give us a compiler error. Let's pass this through GCC. We're going to do that. We are going to finish the build with errors. And if we go up, we're going to find that class animal has no member named do some feline thingy. So this is the compiler error here. This is not going to work. If we need to do something like this, one solution might be to do dynamic casts that we are learning about in this lecture here. And the syntax is ridiculously simple. So we can go down here and put in a simple separator to be able to follow these things on our PowerShell window. You can do this if you want. And we're going to do our dynamic cast. For example, if we wanted to do a transformation and transform this to a dog object, this would give us a problem. And let's try and look at this again. We have a feline object here, and we are managing this through a base pointer. And what we want to do is to take this base pointer and turn it into a dog object. If you look at this, remember that we don't really have any dog information in our feline object. This is going to just go up to the level of feline, but we want to transform this to a dog. To make this super clear, let's look at our inheritance hierarchy again. What we have is a feline object, and the information we have really goes up to this level, and we are managing our feline object through a base pointer. This is the setup we have, but we want to do the transformation and turn this base pointer into a dog object. And this is going to blow up, especially if we have any dog specific member variables. This is going to blow up. This is not going to work. If we try to access dog information through what we get through the transformation to animal to dog, we're going to get a crash because we have no such information. And we're going to look at a simple example to really drive this home. So what we're going to do is go back to our dog class, and we're going to put in a simple member variable. We're going to make it private. And for example, we can make this a member variable to keep track of the speed for the dog. We can do this. And we're going to initialize this to 0 by default. And we're going to set up a function which is going to print some dog information. Let's go back to feline and copy the do some feline thingy method. And we're going to do some dog thingy. That's what we're going to do here. I am going to put in this method and adapt it a little bit. We're going to do some dog thingy, and we're going to account for that in the body. But we also want to print the speed for this dog here. So we're going to say speed, and we're going to print this out. Suppose we have this kind of setup in our inheritance hierarchy here. A dog object has some dog specific information. It has an additional member variable, which is mSpeed here. We won't worry about initializing this from the constructor. You can do that if you want. All we really want is to add some extra data at the dog level. And we're going to see that if we try to transform to dog, this is going to give us a few problems. So what we want is to turn this animal base pointer into a dog object. Let's do this. We're going to change this to dog, and the result object we get is going to be a dog pointer. And we want to call the do some dog thingy method on the pointer we get as a result of this transformation here. Let's see what happens. You're going to see that this is not going to give us any indication that we are doing something wrong. But if the transformation here fails, this is going to silently fail and store junk data in our feline pointer here. And here we're going to try and call a method that is going to possibly use some dog stuff on the feline object. This is going to blow up. Again, we don't have dog information in this feline object. And the do some dog thingy method is going to try and print the speed of the dog that we don't really have. We don't have any dog information. So we have no business accessing dog information from this object to start with. So this is going to blow up, and it's probably going to give us a crash. Let's try and build and see what happens. We're going to pass this through GCC like we always do. The build is going to go through. You see that this is going to even blow up at runtime when users are actually using your application. This is super dangerous. We're going to run this and see what happens. You see doing some dog thingy, and it's going to try and print the speed. The compiler is really trying its best, but this is really going to fail. And we are crashing our program. If you go down here and say done, to make sure we know when the program is done, and we try and run our program again. Let's pass this through GCC to take into account this thing we have on line 20. The build is going to be good. You're going to see that the computer is going to try and really run this, but it's going to see that it doesn't really have any dog information, and the computer is not going to succeed because we are trying to access this dog specific information really on a feline object, so we are going to get a crash. Again, the message is that these dynamic casts can fail, and we need a better way to do some kind of checks before we call our methods here. And we can do this by just using the pointer we get from this transformation here. So we can say if feline pointer and check and see if we have some valid data in this feline pointer. And if that's the case, we're going to do whatever we want to do with this pointer here. Okay, so this is something we can do. And if the transformation fails, we're going to fall in this else block, and we can put some nice message here instead of letting the user crash at runtime. This is much better in my opinion. So we're going to say couldn't do the transformation from animal pointer to dog pointer because we really have no dog information in this base pointer that we have here. This is something we can do. So we're going to say stdc out. We're going to say stdendl here, and we're going to see what happens. Let's build. Hopefully we're not going to get the crash because we are doing something smarter now. We are checking to see if we have any dog information in this pointer before we call some dog specific method on this pointer here. This is the beauty of this. We're going to clear and run rooster. Now you see couldn't do the transformation from animal to dog, and our program is no longer crashing. It is ending properly, and this is much better. This is what you should aim for. So again, the transformations here may fail, but if we turn this back to doing feline transformation, let's do feline pointer. We're going to change this to feline pointer again, and we're going to do some feline thingy now. We're going to build again, and this is true. We're going to build again, and this is going to build successfully, and it is going to properly do some feline thingy. The build is good. We can clear and run rooster. This is going to work just fine, and our program is going to end properly. So here we just saw that we could do a transformation from a base pointer to a derived pointer, and this is going to work just fine. We can also do the transformation for references. Let's say that here. And we're going to go down and put in a simple example to drive this home. We're going to have a feline object. We're going to set up a reference to it. And if we try and call a non-virtual method on this base reference, this is going to blow up because the base class has no information about this non-virtual method that we declare at the feline level. This is going to blow up. If we try to build our program, we're going to see that we get a compiler error saying no such method as do some feline thing. We're going to see that here. No member named this way at the animal level. This is the compiler error we get if we try to call a non-virtual method through a base reference that we have here. This is not going to work. But we can also do a dynamic cast and transform from a base reference to a derived reference, and the syntax to do that is really here. We're going to set up a derived reference. In this case, it's going to be a feline reference. We're going to initialize this with a dynamic cast transformation, and the result of the cast is going to be used to initialize this reference here. And we're going to be taking a base reference and turning that into a derived reference here. This is the syntax. The output you desire is going to be within these angle brackets, and the input is going to be through this parenthesis here. If this succeeds, we will be able to call our method here, and this is going to work just fine. Let's try this out. We are going to put in a separator to be able to follow these things. Let's put that at line 24 here. This is going to do, and we're going to try and build our program. We're going to pass this through GCC. The build is good. We can clear and run rooster. Now we're going to see that we are doing some feline thingy through a reference, and this is super cool. We can do this. You can do this kind of transformation here. And at the end, you see that we are calling our destructors on our objects. And this is a good reminder that we didn't properly release the memory on this animal pointer that we had. So we are going to go down at the end of the program and release that memory. This is good practice. And hopefully you can see how easy it is to forget to release some memory that you allocate for with the new operator. This is a good learning experience here, but we're going to fix this problem. We're going to say animal1, and we're going to release the memory. Now, if we run the program, we're going to see that we are releasing two objects when the program ends. We're going to clear and run rooster, and the destructor is going to be called 2 times. Once for this guy and a second for this guy. This is what we want. And you see that because we have virtual destructors in our classes, we are destroying at each level. So here we are destroying at the feline level, and we are destroying at the animal level. And this is going to properly release the memory from our inheritance hierarchy here. So now you know that you can do a transformation of references using dynamic casts. But with dynamic cast, we have no way to check and see if the transformation was successful. Again, if we try to turn this into a Doug reference, we can do that. And we're going to say Doug reference here. And we will try and call the do some Doug thingy method. This is not going to give us an indication of a problem, but this is going to crash at runtime because we don't really have any Doug information in our original feline object here. So if we try and transform this reference into a Doug reference, this is obviously not going to work because we have no Doug information in this to start with. Let's build and show you the problem. The build is going to be good, so we can clear and run rooster. You're going to see that we are going to terminate our program with a bad cast, and this is going to crash. You see that we don't get to the point where we print done, and we are not even going to get a chance to release the memory that we have allocated in this main function. Hopefully you can see that this is really bad. So with references, we have no way to check and see if the transformation was successful. And this is a limitation. That's why in most cases, I usually do my transformations through pointers. And there is a way you can even turn this base reference into a base pointer, and I am going to show you how you can do that. So we are going to go down here and try to change things a little bit. We are going to say doing proper checks with references, and we're going to put in a piece of code to play with us. And what we're going to do, we're going to take the base reference and turn that into a base pointer. This is the syntax here. Again, the input is a base reference, but the output we desire is a base pointer, and this is possible in C++. This is going to work just fine. Now, we are going to go on top and comment this problematic transformation we just tried to do, and we're going to try and build and see if this is actually working. If this transformation succeeds, we're going to do some feline thingy. If it fails, we're going to say couldn't cast to feline reference, and we're going to say that we are sorry. This is a good output message. If we get something wrong, we're going to build this with GCC and see if this actually works. The build is good. We can clear and run rooster. You see that this is working just fine. We're going to hit the end of the program, and we are going to destroy our objects here. This is super cool. But if we try and do the transformation and transform to a Doug object, even if we know that we don't have any Doug information in this object that we are referencing to start with, we hope that we're going to get a good message and the program is going to end properly. We're not going to get a crash. So let's make sure we are transforming to Doug here. We're going to pass a Doug pointer as our output, and we're going to store this as a Doug pointer, even if the name is still feline pointer. Hopefully this is not going to confuse you. Even if this is named feline pointer, it is a Doug pointer here because we just want to see if we get the error message that we have here. So we are turning this reference into a pointer, and the benefit of this is that a pointer can store null pointers, and we can use this to our advantage to check and see if the transformation here was successful. If it was successful, we will call some Doug thing method. Let's say that here. And if this fails, we're going to say that we couldn't transform to Doug, and this is going to give us a nice message, and our program is not going to crash. We're going to build this again with GCC. The build is going to be good. As you see here, we're going to clear and run rooster. Now you see that we are saying we couldn't cast a Doug reference and our program is not crashing. So if you have a reference to start with and you want to do some proper checks After you do the transformation to a derived pointer or a derived reference, this is the best of both worlds. You can do something like this and your program is going to be much safer. The last thing I want you to see is that these kinds of dynamic casts are really useful if you are passing base pointer or base references into functions. And here I am going to put in a bunch of functions. The first one is going to take a base pointer. The second one is going to take a base reference, and it is going to say do something with animal pointer and do something with animal reference. And inside we're going to do our thing here. We're going to take the animal pointer, turn that into a feline pointer, and we're going to do our proper check, and we're going to do some feline thingy. If the transformation was successful, we can do something like this. We can also do exactly the same thing with references. We're going to take our input reference. We're going to turn that into a derived object, and we can call our method on this pointer. And we're going to do proper checks because we have a pointer which has a concept of null pointer that we get if the transformation here fails. This is the setup we can use in our C++ programs, and we can use these methods to get derived pointers that we can call even non-polymorphic functions on, and this is going to work really well. So we can go down and comment out everything, I guess, to make this super easy to follow, but I don't think we need to comment out everything. We can just comment out what we just did here, and we're going to be reusing the reference we have here and the pointer we have all the way to the top. So we're going to go down and put in a separator here. We can do that. And because of this separator, I don't think we even need to comment things out. We can remove our comment and leave the code in because I want you to see that super easily. And we're going to call our functions here. We're going to say do something with animal pointer, and we're going to pass in animal1, which is a pointer. And we're going to say do something with animal ref. We can do something like this. And we're going to pass in animal ref. We have this reference here, and we can do something like this. You're going to see that this is not going to give us any kind of problem, and it is going to work just fine. Now let's build. We're going to pass this through GCC. The build is going to be good. We can clear and run rooster. And down here, you see that in function, taking base pointer, doing some feline thingy. In function, taking some base reference, doing some feline thingy, and this is working really fine. This is what we want in our C++ programs. This is really all I wanted you to see in this lecture. Hopefully you didn't find it confusing. Again, the message is that you can do dynamic casts to transform from a base pointer to a derived pointer, or to transform from a base reference to a derived reference, as we did right here. But transforming to a derived reference has a drawback in that you don't have a way to check and see if the transformation was successful. So if you want to be able to do checks, you can do something like this and turn a base reference into a derived pointer, and then we can check and see if the pointer is not a null pointer. If it's a null pointer, we will know that the transformation failed, and we will print a good error message. If the transformation was successful, we will have a valid pointer in here, and we will call our derived non-polymorphic method on our pointer. This is going to work really fine. The last thing I want you to see before we wrap up this lecture is that dynamic casts are only going to work with polymorphic inheritance hierarchies. So for example, if we try and turn a double into a string, obviously that's not going to work with a dynamic cast, but let's try and do that to really show you that this is going to give us a problem. We're going to say stdc out, and we're going to put in a separator here, and we're going to set up two variables. One is going to be an int, for example, and we're going to say data. We're going to put in a 45, and if we do a dynamic cast to an std string, for example, that's not going to work. We're going to say std string data str, meaning that this is a string. We're going to say dynamic cast. Let's say we want to turn this into an std string, for example, and the input is going to be our data. If you're trying to do something like this, this is going to blow up. You see that even Visual Studio Code is giving us a squiggly line, so this is not going to work. Just make sure you use dynamic casts in an inheritance hierarchy that supports virtual functions. This is the design purpose for the dynamic casts. If you use this outside this context, you're going to get undefined behavior or even compiler errors if you are lucky. Let's try and build and show you this. We're going to pass this through GCC, and we're probably going to get an error saying that we can't transform from an integer to a string. For example, let's go here, cannot dynamic cast. So basically it is saying dynamic casts are meant to work only with pointers or references. But even then, let's see if we can transform from an int pointer to a string pointer. Let's try and do that. Let's say we want to turn the address of data, or let's set up a pointer to be explicit. We're going to say data ptr, and we're going to initialize this with the address of data. We can do something like this. And we're going to cast data ptr to an std string pointer. Let's see if we can do this, because it is meant to cast between pointers and references, but you see that this is even not going to work. So you shouldn't really do something like this if your input and output are not part of the same polymorphic inheritance hierarchy. Again, dynamic casts are meant to cast from base information to derived information, and the input and output must be part of the same polymorphic inheritance hierarchy. This is the information I am trying to convey here. So this is bad. Don't do something like this. If you do this, you're going to get undefined behavior, or you're even going to get a bunch of compiler errors if you are lucky. This is really all we set out to do in this lecture, showing you that you can use dynamic casts. We are going to stop here in this lecture. In the next one, we're going to show you what happens if you try to call a polymorphic function from a destructor. Go ahead and finish up here and meet me there. In this lecture, I am going to give you a warning, and that is to never call virtual functions from constructors or destructors. I am going to repeat this. Never call virtual or polymorphic functions either from constructors or destructors, and we're going to explore why. We're going to be using this inheritance hierarchy. We're going to have a base class called base. How creative. We're going to inherit from base and create derived, which is our inherited class. And we're going to be using this to explore why we can't call virtual functions from constructors and destructors. This is what our code is going to look like. The base class is going to have a protected member variable. It's going to have a bunch of virtual functions. We will have a virtual function to set things up, and it is just going to set the value of our member variable to 10. And we're going to have a virtual function called cleanup, which is going to maybe do some cleanup. We're going to see how this works out. We also have a method to get the value, but I don't think we will use this, but you can keep this in if you want. Notice that we are trying to call the setup method from the constructor. And you see that we have a comment that says that this is going to do static binding, but we're going to see why in a minute. So this is our base class. We can derive from this class and create our derived class. We're going to inherit publicly, and we are going to override the methods we have in the base class. We're going to override the setup method. As you see here, we're going to override the cleanup method, and our destructor is also going to be virtual because we are good C++ citizens. And this is the setup we have. Once you have your inheritance hierarchy set up, you're going to do something like this. Because you want polymorphic behavior, you're going to set up a base pointer, and you're going to use that to manage a derived object. And you can do something like this. Now, considering this statement here, I want you to think about the order in which constructors and destructors are going to be called. We have touched on this subject before, and we are going to revisit this because it is really important in terms of calling virtual functions in destructors and destructors. So when we do something like this, the base part of this object is going to be built first. So we are going to call the base constructor first. We're going to set up the base part of us. After that, we're going to set up the derived part of us, and we're going to call the derived constructor. And after the derived part of us is set up, we can use our object like we do always. So we're going to use our object to do whatever it is we want to do. When the time comes for this object to be destroyed, we're going to destroy the derived part first, and then we're going to destroy the base part first. Now that we have considered this order, try to think about the setup when we call a virtual function from a constructor. That's what we're going to look at first. The base constructor is going to be called, but notice that by the time we call the base constructor, the derived part of us won't be set up yet. So if we try to call a virtual function in the base constructor, there won't be a derived part to call the most specialized method for. So the compiler will notice that we don't have a derived part yet. We will be at this stage building the base part. And if we call a virtual polymorphic function, we want the most specific part to be called, which should live in the derived part. But we haven't done the derived part yet. We are still building the base part of us. So the compiler is going to notice that we don't have a derived part, and it is going to call the base version of our virtual function. That's why we said that if you call a virtual function from a constructor or a destructor, you're going to get static binding results. If you call a virtual function, you want the most specific version called, but we don't have that yet in the base part because the derived part haven't been set up. That's why we get static binding results. I hope this makes sense. And we're going to get the same result if we try to call a virtual function from a destructor. If we get to the point where our object needs to be destroyed, the derived part is going to be wiped out first. We're going to be left with a base destructor, and when we hit this base destructor and call a virtual function, that would mean to call the most specialized version of that method, but the derived part of our object has been already wiped out. So this is no longer existent, and we are trying to call a method on this. So the compiler is going to do the next best thing it can do. It is going to call the base version of our virtual function. And again, we are going to get static binding results. That's why it isn't really wise to call a virtual function either from a constructor or a destructor. Now, some of you must be asking, what if I really need to do setup and cleanup in the way that we set up these things in our classes? What if this method is really useful? Maybe it is setting up things we're going to be using in our application. We really need this. And the most logical point to call this is the base constructor. Well, you shouldn't really put these in a constructor. What you could do is maybe call this virtual method on your object directly when the object has finished being constructed. That's going to be a better place to do this, because if you put that in a constructor or a destructor, you're not going to get dynamic binding results, and that's going to be really bad. So to sum up, calling a virtual function from a constructor or a destructor won't give you polymorphic or dynamic binding results. The call will never go to a more derived class than the currently executing constructor or destructor, and we will get static binding results. This is the idea I want to convey here. And as a guideline, you should never call virtual functions or polymorphic functions from constructors or destructors. If you really need this, the next best thing you can do is to call your virtual functions directly on your object after the object has been properly set up. We can do something like this and call our setup method, and then we can call cleanup when we think that we need to clean up. And you call cleanup after you construct the object, and you call delete after you clean up your object. This is going to do whatever it is you want to do with your polymorphic functions, and the calls to these virtual functions won't be living inside a constructor or a destructor, and this is going to work really well. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is polymorphic functions and destructors. We should really say with constructors and destructors, but this is going to do, we're going to grab our template files and we're going to put them in place. And we are going to open this little guy in Visual Studio Code by dragging and dropping here. This is going to give us our main CPP file. We can clean up a little bit, remove whatever it is we don't need. And I am just going to put in my classes. I am going to do that in the main CPP file because that's going to be much easier to follow. We have our base class. It is going to have a single member variable called mValue, and we will have a virtual destructor. We will have a bunch of virtual functions. One is going to be setup, which is going to set our value. The other is going to be cleanup, which is going to be doing some cleanup here. We will also have a getValue method, which will get this value and print it out if we want, but it is really not that useful here. We will also create a derived class, which is going to inherit publicly from base. It is not going to have its own member variable. All it's going to do is set up a bunch of overrides for the virtual functions we have in the base class. We're going to override setup, and in derived, we're going to set our value to 100, and we're going to clean up and put a message that we are cleaning up here. Once we have this set up, we can head over in the main function and set up a base pointer, which is going to be managing a derived object. A classic setup for polymorphic behavior. So we're going to say base, and we're going to say pbase, and we're going to say equals new derived. This is going to give us our object, which is managed by a base pointer. And one thing I didn't show you is that we are calling the setup virtual function from the base constructor. This is what we want to see. We want to see what is happening here. Now, if we call this setup function, we would expect polymorphism to kick in because this is a virtual function. If the derived part is available, we will call the most specific setup function, and that would set up the value to be 100 here. If we get the value, that's what we would get. Let's see what we get here if we try to get the value that we have in this object here. So we will get auto value, and we're going to say pbase get value. We have this function here, and we will try to print this out. Okay, this is something we can do in our C++ program, and we're going to see the value we get. Because we are calling this virtual function, we expect polymorphism to kick in, and if polymorphism kicks in, we're going to call the most specialized version of our virtual function here. That would be the override we have in derived, and that would give us 100. So one would get 100 printed out here. But let's see what we get. We're going to run this through GCC, our favorite compiler. The build is going to be good. We can clear or bring up a PowerShell window. We're going to clear now and run Rooster. We're going to see that the base constructor is going to be called. Base setup was called. You see, we called the base version of this. And the derived constructor will be called, and we're going to see that the value doesn't exist. Oh, we didn't put the value out. Let's do that. My bad here. We're going to build again. We're going to use GCC to build, and the build is good. We can clear and run Rooster. Now we see that the base setup method was called and set the value to be 10. And we are really getting static binding results because we are calling the setup method from the base class, and the base version is being called. So this is classic static binding behavior. But we want polymorphic behavior to be working here. But we just saw the reason why this is in the slides. By the time we call this virtual function, we haven't set up the derived part of us yet, and we have no way to call this virtual function which lives in the derived part of us. So the compiler is going to do the next best thing it can do. It's going to call the base version of this method, and we are going to get static binding results. And we are going to get the same results if we try to call a virtual function from the destructor. For example, if we go in our destructor here, let's see if we can find it. We're going to go in our destructor here and say this and say cleanup. You can do something like this. And you're going to see that the cleanup version we call is the base version of cleanup. And we don't really want to do something like this. We want the most derived cleanup version to be called, but we won't get that because by the moment we call this virtual function from our base class, the derived part will already have been wiped out, so it won't be available. And the compiler will do the next best thing it can do. It is going to call the base version of our cleanup function here. I hope this makes sense. Again, to really drive this home, I realize this can be confusing to many people, especially beginners. If we are calling a virtual function from a constructor, we will call that virtual function when we hit the base constructor. But by the time we hit the base constructor, the derived part of us hasn't been constructed yet. So if we try to call a polymorphic function, needing to call the derived implementation, that won't be available, and the compiler will do the next best thing it can do. It is going to call the base version. The same phenomenon is going to happen in the destructor. When we are done using our object, we will destroy the derived part information first. And when we hit the base destructor and call a virtual function, there won't be a most specialized version of the virtual function because the derived part has been already destroyed and it doesn't exist anymore. So if we call a virtual function from the base destructor, we will get the base version called, and this will give us static binding behavior. This is what we are experiencing here. Okay, so let's try and run this program and see what we get. We will print our value here, which is going to give us static binding results, but we want to see which version of cleanup is called. This is what we want to see here. We're going to run the task to build with GCC. The build is going to be good as usual. We're going to clear and run Rooster. And we're going to see base constructor called, derived constructor called, and we're going to have a value, which is a junk value because we never initialized this value, but we don't see our destructors called. What is going on here? Let's investigate this a little more. The reason is we are not explicitly releasing this memory here through the base pointer. Let's do that. We're going to delete pbase here, and we're going to run again. We're going to build with GCC. Now our destructors should be called. We're going to run Rooster, and we are going to see that the base cleanup version was called, and again this is giving us static binding results. You don't want something like this. So if you want to get this behavior, I would advise not to call the cleanup or setup functions inside constructors or destructors. And that's the guideline I gave in the slides. You should really never call virtual functions either from constructors or destructors, especially if you are doing this from a parent class, hoping to get the most specific virtual function called through polymorphism. If you want to do that, the best thing you can do is to call the cleanup functions and is to call the setup and cleanup functions after your object has been properly constructed or before your object gets to be destroyed. So what you can do here is call the setup method on the pbase pointer here. Let's do that, and we're going to call setup. This is going to call our virtual function, and we are going to get polymorphic behavior. This is going to print a 100 as we expect because it will call the derived version of setup here. And before we delete our object, we will need to call the cleanup function if we need to do some custom cleanup here. So we're going to say base and call the cleanup function, and this is going to give us the behavior we want. We're going to build our program, pass this through GCC. The build is going to be good. We can clear and run Rooster. And we are going to see that base constructor was called, derived constructor was called. We will call the derived version of setup. Our value will be 100. And when we get to release or clean up our memory, the derived version of cleanup will be called. And then we will destroy the derived part of us, and then we will destroy the base part of us. And this is going to work in line with the behavior we are familiar with polymorphism, and this is really cool. So this is what you should do. You should never call virtual functions from destructors and constructors because that's going to give you static binding results, and what you want in this case is really dynamic binding behavior. This is really all I had to share in this lecture. I hope you found it interesting. We are going to stop here in this one. In the next one, we're going to learn about the type ID operator that can come in handy, especially if you want to debug polymorphic code in your C++ program. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about pure virtual functions and abstract classes. And pure virtual functions are a mechanism we have in C++ to mean that the method isn't meant to be implemented in the base class. Here we have a simple inheritance hierarchy to try and drive this home. The base class is shape, and we are deriving from this class to create a circle class. And on the other side, we are deriving to create a rectangle class. If we look in the shape class, we have two virtual methods. One is going to be used to compute the perimeter of the shape. The other is going to be used to compute the surface of the shape. But if we go down in our inheriting classes, we're going to see that we have the same methods. These are going to be overrides of what we have in the base class. But the special thing about this inheritance hierarchy is that we don't have implementations for these methods in the base class here. And this is by design. If you think about it, this is an abstract shape. We don't know if it's a rectangle. We don't know if it's a circle. We don't know if it is a triangle. So we don't really have concrete information we can use to properly compute its perimeter and its surface. So it makes sense to really leave in the declaration for these methods, but leave the implementation details to inheriting classes, because these classes are going to have concrete information we can use to reliably compute the perimeter and the surface, and we can get this information here. So in C++, we mean this kind of design by setting up these methods as pure virtual functions. And what this is going to tell the compiler is these methods are not meant to be implemented in the base class. They are meant to be overridden and implemented by inheriting classes. And another side effect of this is that the compiler is going to prevent you from creating objects of this class, because it really doesn't make sense to create an object of shape in your design if you won't be able to compute its perimeter, if you won't be able to compute its surface. So why bother creating an object that you won't really be using in your C++ program? The meaning for this base class is just to be an idea or a representation of a shape without really going into the concrete implementation of how that shape really works. Hopefully this makes sense. So let's see how we can do this in code. Here we have a simple class, which is going to be our shape class. We are going to have two virtual functions. We're going to have the perimeter function. We're going to have the surface function. These are going to be virtual functions or virtual member functions, I should say. But we are going to make them pure virtual functions by using the syntax you see here. So we're going to prepend n equals 0. And this is going to tell the compiler that these are pure virtual functions. Once you set up these functions, a few things are going to happen in your class. This class is going to become an abstract class in that you want to be able to create objects of this class anymore. If you try to do that, you will get a compiler error. Another thing is that you don't need to put in implementations for these methods because you marked them as pure virtual. And what this means is that the implementations will be put in by inheriting downstream classes because they will have concrete information to compute the perimeter or the surface as we have here. So we don't need to bother with definitions for these functions here. If you even try to put in a definition here, you're going to get a compiler error because this is a virtual function. We have no business putting an implementation in the base class here. These are meant to be implemented by downstream inheriting classes. Okay, once we have our shape class and our inheritance hierarchy, we can try to run this in our code. For example, if we try and create a shape object, we're going to get a compiler error because shape is an abstract class, so we can't create objects of it. And I don't think I made this super clear. Once you set up at least one pure virtual function in your class, the class is automatically going to become an abstract class. And what that means is that you want to be able to create objects of this class. So this is an abstract class we have here. And if we try to create an object of it, as we are doing on this line here, this is going to give us a compiler error. But we can still use a base pointer to manage a derived object, a common setup we do with polymorphism. So for example, here we can set up a shape pointer and use this to manage a rectangle object. If we call the surface member function on our base pointer, this is going to do a polymorphic call, and we will get the surface of the rectangle. And we're going to print this out here. You're going to see that this is going to work. We can also use a base pointer to manage a circle object as we see here. If we call the surface method, this is going to do polymorphism, and it is going to call the surface version of the circle class, and we can see it printed out here. This is the design we can achieve. Even if shape is an abstract class, we can't create direct objects of shape as we are doing here, but we can use a base pointer or a shape pointer to manage derived object through polymorphism. And you need to be aware of this. Okay, now that you have an idea about what a pure virtual function is and what an abstract class is, let's see a few ideas you need to keep in mind. If a class has at least one pure virtual function, it will become an abstract class. You already know this. You can't create objects of an abstract class. If you try to do that, you will get a compiler error. Another thing I don't think I made super clear is that derived classes from an abstract class must explicitly override all the pure virtual functions from the base class. If you leave in any pure virtual class that you don't put in an implementation in for, your derived class is also going to become an abstract class, and you want to be able to create objects of it. You need to keep this in mind. Another thing you can't do, you can't call the pure virtual functions from the constructor of the abstract class. If you do this, you're going to get a compiler error because we don't have implementations for these things. So this is not going to work. The constructor of our abstract class is used by deriving classes to build the base part of our derived objects, but they are not meant to be used from the outside because we can't really create an object of an abstract class. So now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is Pure Virtual Functions and Abstract Classes. We are going to grab our template files and put them in place, and we're going to paste them in this project here. And we are going to grab the files that make up our inheritance hierarchy. You are going to get these files from the resource section of the course. If you want, you can download them and use them like I am using them here. Or even better, you can type the code and see how these things really work. That's the best way to learn. I do recommend that. But we want to save on time here, so I am just going to reuse these classes that I have lying on my drive. I am going to open this in Visual Studio Code by dragging and dropping here. We have our shape class here. This is going to be our base class. You're going to see that we have our member variable, which is going to be the description for our shape. We have a bunch of constructors here, but the most important thing here is that we have a bunch of pure virtual functions here. And if you go in the CPP file, you're going to see that we don't have implementations then for the perimeter and surface functions. These are pure virtual functions, and we have no business putting in an implementation in the base class. Once we have these virtual functions in and mark them as pure virtual functions, by prepending n equals 0 here, this class here is going to become an abstract class. And what that means is that we can't create objects of this class. It is meant really to be inherited from, and downstream inheriting classes are going to be forced to override these methods here. Otherwise, they are themselves going to become abstract classes. We're going to have a chance to look at this here. We also have our rectangle class, which is going to be inheriting from shape. It is going to override our two methods. We're going to override the perimeter function. We're going to override the surface function. For rectangle, the perimeter is computed this way. We're going to multiply the width by 2 and the height by 2, and we're going to add these two things up. We're going to compute the surface by multiplying width and height, and this is going to give us the data we want. We can look at circle. It is going to also inherit from shape, and it is going to override our methods here. If we want, we can even put in a radius and a variable to keep track of pi. We can do this. You can really do this however you want. This is just going to allow us to compute the surface relatively easily in this class here. Let's look at the implementation. Nothing special here. This is just going to forward the construction of the base part of us to the base constructor, and this is going to do whatever it is we want to do here. Let's head over to the main CPP file and actually use these things. We are going to include circle and rectangle. Let's do that. Circle.h, and we're going to put in rectangle.h, and we're going to first try and create a shape object. Let's do that. We're going to say shape and say shape pointer, and this is going to be new shape. We can use a default constructor, and if we do something like this, you're going to see that we're going to have a compiler error here. We have a squiggly line, but if we bring up a terminal window and look at the problems tab, we're going to see that object of abstract class type shape is not allowed. So shape is an abstract class now. And why is it an abstract class? Because we have at least one pure virtual function here. We actually have two, and this is going to make our shape class an abstract class. What that means is that we can't create objects of this class, and if we do that, we're going to get a compiler error. Let's try and build this program. We're going to pass this through GCC, our favorite compiler. We are going to see that the build is going to fail. We're going to have a bunch of errors. If we go up and look at the error we have, invalid new expression of abstract class type shape. So we can't really create an object of this. Let's go down and see what these errors are saying. Note, because the following virtual functions are pure within shape, and they are going to try and really be helpful in the errors that they give here. And all they are saying is that we can't create objects of this class because we have pure virtual functions inside. Okay, now you know this. If a class is abstract, you can't create objects of that class, but you can still use a base pointer to manage derived objects of that class. So let's comment this out because this is going to make our code not compile. And we're going to say that this is going to give us a compiler error. And we're going to try and use a base pointer to manage a rectangle object. We can do this. So we're going to set up a shape pointer, and it is going to be managing the memory of a rectangle object. We're going to go through the base pointer and call the surface method. And this is going to call the implementation in rectangle because our base pointer is really managing a rectangle object. If you want, you can even use the type ID operator to print the dynamic type of this shape rect pointer. You're going to see that it is managing a rectangle. You can actually do this because we learned about that in the last lecture. So let's practice that. We're going to say dynamic type of shape rect, and we're going to say type ID, and we're going to dereference the pointer. We're going to say shape rect, and we're going to print the name of this, and we're going to see it print out on our PowerShell window. And after this, we are going to print the surface that we got from this call here, and we're going to see what this gives us. Let's try and build this program. We're going to pass it through GCC, our favorite compiler. The build is going to be good. We're going to clear and run Rooster. We're going to see that the dynamic type is rectangle. You can see that right here. So the base pointer is really managing a rectangle object, and this is what we have here. And if we call the surface method, we will be calling the method on the dynamic type. So we will be calling this surface method on the rectangle class, and we will be using the implementation we have here. So the surface function that is going to be called is what we have on line 20 in rectangle here. And this is going to just be a multiplication of width and height, and we're going to get 100 here because our width and height happen to be 10 and 10. So multiplying this is going to give us 100 as we see here. This is really cool. This is what we expect. We can even use our base pointer to manage a circle object. So let's do that. We're going to put in a separator to be able to follow this easily in our output. So let's say stdndl here, and we're going to put in the code. So we're going to set up a base pointer, which is really going to be managing a circle object here. And we will call our surface method. This is going to call this method polymorphically because surface is a virtual function. So we will get polymorphism here, and we will call the surface method on the circle object, which is really our dynamic type. If we print this out, we're going to see the surface printed out. But if we want, we can even print the dynamic type of our base pointer here. So we're going to do the same thing we did for rectangle. We can use our type ID operator to print the dynamic type of shape circle. And we're going to say shape circle here. And this is going to do what we want. Let's look at this. We're going to be printing the surface here. This is exactly what we want. So let's build and run. We're going to pass this through GCC. The build is going to go through as you see here. If we clear and run Rooster, we're going to see that the dynamic type is now a circle. So the base pointer or the shape pointer we have here is really managing a circle object polymorphically. So if we call a virtual function on this base pointer, it is going to call the most specific implementation of the surface object we have, and that happens to be for this circle object here. This is what I mean. If we compute the surface, we're going to see that it is going to be using the data we have here, and we will get this number as our surface. If you plug this in, you're going to see that this is really right. So this is really all I had to share in this lecture. We can set up pure virtual functions in our base class, and what that's going to do, it is going to make our class an abstract class, but we won't also be able to put in implementations for these methods anymore in the base class because they are meant to be overridden and implemented by downstream inheriting classes. So if you go in here and try to put in an implementation, we will probably get a compiler error because this is not allowed. You see, we have a problem here. If we try to build, we will get a weird compiler error. Let's make sure we see the compiler error. So build finished with errors, and we are going to see what's the problem here. Let's go up and see pure specifier on function definition. So this is not allowed. So we are really conflicting ourselves here. we are marking this function as a pure virtual function. And what that means, and a pure virtual functions isn't meant to have a definition, but we are also putting in a definition here. So the compiler is going to be confused. This is not something we should be doing. Another thing I want to point out before we wrap up this lecture is that downstream inheriting classes are forced to override and implement all the pure virtual functions from the class that they inherit from. If they don't do that, they are themselves going to become abstract, and we want to be able to create objects of them. So let's try and, for example, comment out the surface implementation here. And that's going to make our circle class an abstract class. And if we try to create an object with circle, we will get a compiler error because now circle is an abstract class. Let's try and build and show you the compiler error. And this can really be confusing if you are a beginner on this. You will be wondering why you can't create objects of your class even if you didn't really explicitly put in any pure virtual function. The reason is we are inheriting from an abstract class that has two pure virtual functions, but we are only overriding one pure virtual function. We need to override all of them. Otherwise, our class is also going to be an abstract class. Let's look at the compiler error we are getting here. Let's go up and see if we can find it. We are going to say in function, in main, invalid new expression of abstract class type circle. We are trying to create an object from an abstract class. This is the error we have here, and you should really know this. So let's go back and make sure we are overriding all these things, because we need to do that to be able to create objects of a circle. And now this is going to work exactly as it should. Let's build and make sure of that. The build is going to be good. We are fine. This is working exactly as we want. This is really all I wanted you to see in this lecture. I hope you found it interesting. We are going to stop here in this one. In the next one, we're going to learn about interfaces in C++, and they are going to be reusing the knowledge we learned about in this lecture. Go ahead and finish up here and meet me there. In this lecture, we're going to see that we can model interfaces in C++ using abstract classes. I know there's a lot of things that might not make sense in what I just said, so let's break this apart. An interface can be thought of as an abstract class with only pure virtual functions and no member variable. So if you have a setup like that, you can call that thing an interface. Let's look at a simple example here. Here we have a simple class called streamInsertable. You see that it doesn't have any member variable. It only has a pure virtual function here and a helper function that we could set up to help us do a few things. The only specification to make this an interface is to have in only pure virtual functions and no member variables. If you have in a member variable, this is going to stop becoming an interface in C++. Okay, so you can think of an interface as an abstract class with at least one pure virtual function and no member variable. That's going to make it an interface. Down here, you see that an interface can be thought of as a specification of something that will be fully implemented in a derived class, but the specification itself is going to reside in the abstract class. Another way to think about an interface is to treat an interface as a thing you can attach to your types to give them superpowers. For example, this streamInsertable interface has a single job, and that's going to allow our types to insert data into output streams like stdcout. This is the only thing this interface is going to add to our types. So we can take this interface and attach that to a point class, for example, and we will automatically be able to print point objects to the output stream, and we won't need to overload the stream output operator in the point class. We can do the same thing to our bird class, we can do the same thing to our dog class, and we will be able to print these things without having to overload the stream output operator. Hopefully you can see how powerful this is if we manage to set up this kind of relationship between our type and our interfaces. So again, an interface is something you can attach to your types to give them powers or features that they originally didn't have. And that's going to save you from having to implement these features separately in each class for your time. So this is a huge time saver. Now you must be asking, how do I take my interface and attach it to my type? Well, the way C++ does this, you have to inherit from the interface from your type to attach the interface to your type. So for example, if we wanted to attach this interface to our point class, what we would do is something like this. We would set up our point class and inherit from our interface, which is stream insertable. The moment we do this, our point is going to be able to print things to the console through the stream output operator. But hopefully you can see that something is missing. How does our point class know how to print stuff? If we go up and look at our stream insertable interface, we're going to see that it is declaring a stream output operator. It is this thing that is used to print data to the output stream. You see, this is a regular output stream operator. We will be printing to std_o_stream, and the object is named out here, and we will be printing whatever operand that is passed as a second parameter here. But the catch is, we will need to set up a virtual function that will need to be implemented by whoever inherits from our interface here. And this is going to be super powerful. We are going to take over the job to print to the output stream, but we will let inheriting downstream classes to specify what we print, and they are going to specify that in this virtual method. Let's look at our point class again and really put the puzzles together here and understand how this works. Okay, this is our point class, and it is going to be inheriting from our interface, and it is going to implement our virtual function here. We are going to set it up here, and we are going to mark it as an override because it is overriding a method that comes from our stream insertable interface here, and it is going to specify which data we print to the output stream and how the data is going to be printed out. You can specify these things here. We're going to format the data in a point, and we're going to be using these square brackets to put mx and my here. And notice that this is an override, so the inheriting class has all the information we need to put in our output stream operator, and we will do that through our stream insert override here. Now let's go back to our stream insertable interface to see how our output stream operator actually works. What we have here is what would be a header, and this is going to just put in a declaration for this, but we can even look at its implementation. The implementation for our output stream operator may look something like this. We are going to pass in the first operand and the second operand here, but notice what we are doing here. We are going to call the stream insert virtual function on our operand here, and this is going to call the most specific implementation we can find for the stream insert. If we are trying to print a circle, for example, this is going to call the stream insert override on our circle object. If we are trying to print a point, this is going to call this method on our point object. And this is going to use polymorphism because our second operand here is passed by reference. Hopefully you can see how this is super powerful. I know this is convoluted because we are jumping around trying to explain this, but I couldn't really come up with an easier way to put this. We have to try this in code to really see the power of this. But this is really the power of interfaces. We can design our features and wrap them in an interface, and we can really attach that interface to any type we have in our C++ program, and that type is going to automatically inherit the features that we have set up in our interface. For example, now that we have attached this interface to our point here, we can print our points on the output stream, and this is going to work automatically. You see that we don't need to set up an output stream operator on our class altogether. We can even go further and attach this interface to a full inheritance hierarchy. For example, if we have our base class to be animal and we inherit from this class to create all kinds of crazy classes, we can go on and attach our interface to the base class here. And this is going to make all our classes in our inheritance hierarchy have the features that the interface has brought to the base class here. So for example, we can attach our interface to the animal class by inheriting from stream insertable here. And this is going to give our animal the powers to be printed out to output streams, And this is going to be powered by the virtual function that we are overriding here. You see, we are going to specify which data to print in our animal class and how the data is going to be printed out here. And we can do that in this override. And this is super powerful. Once we do this, we're going to go to each class in our inheritance hierarchy and implement the stream insert override. Because if we don't do that, this class is also going to become an abstract class because it is inheriting from a class that has a pure virtual function. Remember, if you inherit from a class that has at least one pure virtual function, you will be forced to implement all the pure virtual functions that come from your parent class. If you don't do that, you are going to become an abstract class yourself, and we don't really want that. That's why we are overriding the stream insert override here. And with this, we are going to specify which information to print from our object here. In here, we are going to put out the description and the wing color. And this is the format we specify here. And this method is going to be called by our output stream operator, which is coming from our stream insertable interface. Hopefully you can see how this is super powerful. Okay, now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is abstract classes as interfaces. We're going to grab our template files and put the data in place. And we're going to copy this and put that in here. We are going to put in the files we're going to be using in our inheritance hierarchy. You see we have our animal hierarchy here. You can grab these files from the resource section of this lecture and you can reuse them like we are using here. Or if you want, you can even type this, but I don't really recommend this because this is too much typing. We just want to learn about interfaces here, and that's what you should focus on. So we're going to open this up in Visual Studio Code, and this is going to give us all the files we need. We're going to look at the top class, and we will see that it is inheriting from our stream insertable interface. So let's look at our stream insertable interface because this is the focus of this lecture here. So it is a regular class as you see here. It is class stream insertable. We're going to set up an output stream operator, and it is really like any other output stream operator you have seen. We're going to pass the second operand by reference, and we are going to specify our pure virtual function, which is going to be implemented by downstream inheriting classes from this class here. And this is going to set up polymorphism, and what this will do is if we call this method on our second operand here, we are going to call this method polymorphically. So if we are trying to print a point, we are going to call this method on a point object and we will print it out exactly how the point wants to be printed. If we are printing a circle, we will call this stream insert method on a circle and we will print a circle exactly how a circle wants to be printed out. Let's look at the implementation, and it is nothing really complicated. We're going to specify our output stream object as a first parameter here, and the second parameter is what we want to print out. We will pass this by reference, and this is going to allow us to do polymorphism. Remember that stream insertable is really going to become our top base class. So we will basically be setting up stream insertable polymorphism here. You need to keep this in mind. We are going to call our stream insert method on our operand, and we're going to pass the stream output we want to print on, and we're going to return this output stream to really make this behave like a regular output stream operator to allow output chaining in our operator here. Once we have this stream insertable interface, we can really use it however we want. Let's head over to the main CPP file and try to play with us. So what we are going to do is crack this open, and we are going to remove whatever it is we don't need. We are going to include our interface, so we're going to include stream insertable. Let's do that. Insertable.h, I think this is the name. And we're going to set up a point class which we wish to be printed out on the output stream. Notice that we want to inherit from stream insertable, and what this is really doing is attaching the interface to the point class here. And because this stream insertable interface has a pure virtual function, we need to override this pure virtual function here. If we don't, we want to be able to create objects of our point here. Let's go down and show you that we're going to get that problem. If we don't do that, we're going to say point and say P1 and, for example, put in 10 and 20. We will have a compiler error because now the point class is an abstract class because it is inheriting from a class that has a pure virtual function and it is not overriding that pure virtual function. So in other words, this class still has a non-implemented pure virtual function. That's why it is an abstract class and we can't create an object of it. If we're trying to run this code, we're going to pass this through GCC. We will get a compiler error. Okay, we have a compiler error here and we need to fix this. All we need to do is to implement the interface that comes from our stream insertable interface here. So we can grab our pure virtual function and implement it in our main CPP file for the point class. We're going to put it in here and we will remove the pure virtual function specifier here and we will put in an implementation. We want to specify that this is an override of a method that is coming from our upstream parent class. And we are going to head over in the body of our function and put in the information we want to put out. This is a point object, so we just want to print the mx coordinate and the my coordinate here. And this is the format that we want. And at this moment, the job of this function is really done and it will be picked up polymorphically if somebody tries to call this on a point object through polymorphism, and this is going to work. Now that we have this point, we can try and build and make sure this is working. Let's make sure we don't have the compiler error anymore. The build finished successfully, so we are cool here. But what we want to see is that we are able to print point objects, because that's the whole point of attaching this interface to our point class here. So what we are going to do is print this out. We're going to say stdc out. We're going to say p1 and we're going to say p1 here. This is how we would use our output stream operator. You see, we don't have a compiler error. This is really magic. Some of you are going to ask, how is this even working? Somebody is going to look at your class. They are going to look, you don't have an output stream operator, but you can print your objects. So how is this working? Well, this is working through the magic of interfaces. We are attaching this interface to our point class, and this is going to give our class the powers that come from this interface. And one of those powers is to use the output stream operator we get from this interface. We can use that directly. And what this is going to do, let's look at the implementation of this interface. This is going to just call the stream insert virtual method on the object that we pass as a second parameter in this operator here. And the second parameter happens to be the point that we are printing here. So what this is really going to do is something like this. We're going to try and figure out what the compiler is going to try and do. We are going to say P1 and we're going to say operator stream output and we're going to say stdc out. That's the stream we want to be printing to, and the point we want to print is P1. This is basically what the compiler is going to do, and it is going to print our thing. And this method is available in our stream insertable header, and it is a friend of our interface. That's why we are able to do something like this, accessing the data from our interface. Let's build and actually show you that this is going to work. We're going to pass this through our GCC compiler. The build is going to be good, so we can clear, not clear. We're going to Control Z on this, and we're going to bring up a PowerShell window, and we're going to clear this time and run Rooster. You see that we are printing our point here, and this is really cool. We can even uncomment this. And we're going to use stdc out because the compiler is going to take this and turn that into this. And we have the ability to have code that is much more readable by C++ developers out there. We're going to build and run this again. The build is going to be good. We can clear and run Rooster. And this is going to print our point here. And this is really cool. But this is not the end of our story. We can even print an entire inheritance hierarchy. Look at what we did at our animal class here. We attached this interface to our animal class, and the moment we do that, we need to override the pure virtual function that comes with this interface. And that's what we did down here. We have overridden the stream insert virtual function, And in the body, we're going to specify which data we want to print and how to print that data. That's the whole point of this override we are doing here. We are going to do the same thing in each inheriting class from animal. For example, if we go to feline, we're going to do exactly the same thing. We are going to inherit from animal, and this will indirectly inherit from our interface. So we need to override the pure virtual function that comes with that interface, and we do that here. We're going to specify which data we want to print. In this case, we're going to put the description out and the first style. And we are going to specify the format in which we want the data to be printed out. Again, that's the whole point of overriding this virtual function here. We're going to do the same thing on each inheriting class in our inheritance hierarchy. For example, we did the exact same thing for dog. We did the exact same thing for cat. And we're going to do the same thing on our bird classes. That's exactly what we do here, specifying which data to print out and how the data is going to be printed out. And this stream insert override is going to be picked up by our interface when we get to call the output stream operator here. Notice that we are calling this thing polymorphically. We are calling our stream insert method on a reference that we pass here, and this is going to resolve this using dynamic binding, and this is going to work really well. Now that we have this set up, we can head over to the main CPP file and really do all kinds of crazy things. Let's put in a separator here, and we are going to play with us. We are going to include the classes we need to set up our animals, and we're going to put them in here. We have animal, feline, dog, cat, bird, pigeon, and crow. The moment we do this, we don't need to put in this stream insertable because it is coming in directly from this, but we don't need to worry about this because we have include guards in. But we are going to be using smart pointers, so let's include the memory header, and we can set up an animal and try to print it out. We will be using polymorphism, so we will go through a base pointer to animal and use that to manage a dog object here. We are just going to pass in the data and we will try to print this animal out. Notice that we are going through a base pointer calling the output stream operator, so this is going to resolve the call to stream insert polymorphically, and it is going to print this information at the dog level. And what I mean by that is that if we go in dog, we're going to find our stream insert. That's going to print this information here like we want to print a dog. And this is super powerful. Hopefully you can see how cool this is. We're going to try and build this program. We're going to pass this through GCC. The build is going to be good. We can clear and run Rooster. We're going to see that we print this as a dog, even if we used a base pointer to try and print this out. How cool is this? We can even use this to set up a bird and print it out. We're going to set up a base pointer that is going to be managing a bird. You can see that we are using a unique pointer here. You can really use any kind of smart pointer you want. We're going to print this out, and this will be printed out like a bird wants to be printed out. And that's going to be using the override from our bird class, and that's going to say bird is going to put out the description. It's going to put out the wing color, and this is really going to work really well. We're going to pass this through GCC again. The build is going to be good. We can clear and run Rooster. You see that we are printing our bird here, and this is using polymorphism combined with interfaces, and this can come in handy if this helps your application depending on what you want to achieve with C++. We can even put our animal data in an array and try to print that out. So we're going to put out a separator to be able to follow this nicely in our output terminal. This is going to do, and we're going to go down and put in the code to play with us. We're going to share up an array of shared pointers. This is how we do this. And we're going to initialize this with all kinds of crazy animals. We're going to put in a dog, we're going to put in a cat, we're going to put in a crow and a pigeon, and we will be managing this through base pointers. Notice that this is an array of base pointers, and we're going to be calling the output stream operator polymorphically. So for the first element here, we will print a dog, how a dog wants to be printed out. So we will be using the stream insert override from the dog class. If we go there, we're going to see that we're going to prefix our data with dog. If we hit the second element, we're going to print this like a cat wants to be printed out. The third element is going to be printed out as a crow. The fourth element is going to be printed out as a pigeon, and this is going to fall in and work right away. Down here you see that we are looping, calling our output stream operator, and this is going to work really well. Let's try and build this program. We're going to pass this through GCC. The build is going to be good, so we can clear and run Rooster. And you're going to see that we are printing our information here. The first thing is a dog. The second thing is a cat. The third thing is a crow. The fourth thing is a pigeon. And this is working really well. Hopefully you can see how interfaces can be powerful in your C++ design. Use this if it makes sense for whatever application you are designing with C++. My main goal here is to introduce you to the idea of interfaces and how powerful they can be. Again, an interface is something you can attach to your type in C++, and at the moment you attach that interface to your type is going to have the powers that come with that interface. And all you need to do in your deriving classes is to implement the virtual functions that come with that interface, and the interface will pick them up and use them to do whatever it is you want to do polymorphically, and that's going to be really cool. We are going to stop here in this lecture. The next one we're going to try and recap what we saw in this chapter. Go ahead and finish up here and meet me there.